Hello students, welcome to the class. So today we will see the theory part 3 of the chapter 6 equilibrium, in which we will cover the section 6.3. Now this is the disclaimer. Our objective would be to see the expression for equilibrium constant. Now we are already introduced with the equilibrium concept. We need to quantify this thing, and to quantify this thing we search for a constant which is equilibrium constant. We will see the derivation also, how do we derive it and how do we apply it on the given equation. If I talk specifically about the NCERT section, so I have told you we are going to cover 6.3, which is law of chemical equilibrium and equilibrium constant. After that we will do some questions also of the NCERT, which is 6.1 and 6.4. Then I have put up a practice problem for you. We will try to solve the problem with the help of this 6.3 section. So first, let us see what is equilibrium constant. Now to understand that, you must know what is law of mass action. According to this law, whenever you are considering a reaction, then the rate of that reaction is equals to the product of reactant concentration, where each concentration term is raised to its stoichiometric coefficient. Now what is the meaning of this? Suppose you are doing a reaction. So your reaction must have a rate. So rate can be considered similar to the speed. Suppose you are running a bike, the bike is running at some speed. So if your reaction is going on, it must be going on with some speed or some rate. Now this rate is totally dependent upon the reactant concentration according to the law of mass action. And what is the variation? How does it vary? How does the rate vary according to the concentration? So it varies according to the stoichiometric coefficient. Now, if you are trying to apply this law of mass action, then you will be able to find the Kc. Suppose we have a hypothetical reaction which is A plus B giving us C plus D, where small a and small b, small c and small d are the stoichiometric coefficient of the respective reactants and products. Then applying the law of mass action for the forward reaction, we can get Rf is directly proportional to concentration of A raised to the power small a, concentration of cap B raised to the power small b. Then upon removing the equilibrium, upon introducing the Kf, we can remove the this proportionality sign, and the Kf, which is the proportionality constant, is the rate constant for the forward reaction. And what are A and B are concentration of reactant. So we can represent the concentration by writing A and B in the square brackets. Similarly, if you write it for the backward reaction Rb, then applying the law of mass action, we can say that for the backward reaction our reactants will be C and D. Now according to this equation, we will write that C and D are the concentration of product C and D respectively. Now here is a confusion. You would say that okay, we are telling that C and D are products, but you are also telling me at the same time that C and D are the reactants. Now this is basically product, your C and D are products with respect to the given equation, which is this equation. But when you are considering it for the backward reaction, your product become the reactants, which is C and D, and again they will be raised to the power small c and small d, which are their respective stoichiometric coefficient. Again, when you will remove this proportionality sign, you will introduce a proportionality constant, which is Kb, which is rate constant for the backward reaction. Now if you got the rate of forward reaction, the rate of backward reaction, can we apply this same to the equilibrium condition? Yes, we know that at equilibrium, your forward and backward rate becomes equal, and that is the reason we don't see any net change in the physical quantity, because the rate of formation of product and the rate of depletion of reactant becomes equal. Okay, so Rf will be equals to Rfb. Now substituting this value of Rf and Rb, we will get Kf multiplied by concentration of A raised to the power small a, then concentration of B raised to the power small b. This will be equals to Kb. Then we have C raised to the power small c and D raised to the power small d. Can we deduce this further? Yes, we can find the ratio of Kf to Kb, which is concentration of the product divided by the concentration of reactants, where each of these concentration terms is raised to the stoichiometric coefficient. Further, what we do, we take this Kf by Kb as Kc. Now we call this Kc. Here remember we are taking the capital K and the Kf and Kb are having the small k. So here the Kc is called as the equilibrium constant, and the expression that we finally got is Kc is equals to concentration of product by concentration of reactant, where each concentration terms are raised to the stoichiometric coefficient. So this is the most important equation of today's session, and it is equation number 6.4 of the NCERT. Then what are the things that are present? Kc is the constant and it is specified at a given temperature. We will see that what all the things on which the equilibrium constant depends, and you will see that there is only one function, which is temperature, which decides the equilibrium constant. Second, we have our concentrations. Now these concentrations are only validated at equilibrium. Okay, so you will not take any random concentration. You will take only that concentration where this given reaction attains the equilibrium. Then the C in the K describes the equilibrium constant in terms of molar concentration. Now there are many varieties of this equilibrium constant. You can take Kp, which is equilibrium constant in terms of partial pressure. You can take K chi, where K chi will represent the mole fraction, right? Which is equilibrium constant in terms of mole fraction. So there can be various situations, but here we have derived it for the equilibrium concentration, molar concentration. Now what are the factors that affect our numerical value of Kc? The first is, if you are adding two reactions, then you will see a change in the Kc. If you are reversing the reaction, and if you are changing the stoichiometric coefficient. So basically here are the factors which are changing your reaction, and these factors are changing your stoichiometric coefficient of the balanced chemical equation. So directly you can say that whole value of Kc is dependent upon the equation. So equation is a very, very important part. Let's see how. Suppose we take the first case, which is addition of two reactions. Then what we can say? We can take two hypothetical situations. First is A is going to B, and for that the equilibrium constant is K1. We can write it as B by A, concentration of B by concentration of A, and it's very obvious. You already know the law of mass of action. We have applied onto the equilibrium constant founding, and we have said that if you want to find the equilibrium constant, you have to take the concentration of product divided by the concentration of reactant. Further, if you apply it onto a second situation, which is equilibrium between the reactant B and the product C, then you can write K2 is equals to C by B, where K2 is the equilibrium constant for the second reaction. And for the third situation, suppose we take K3, which is concentration of C divided by concentration of A. So this is from A going to C. Now if I ask you, can you get the third equation using the first and second? Yes, it's very easy. Just add above two equations. If you add both of these equations, this B and this B will get cancelled out, and you will get a direct conversion from A to C. But what will happen to the equilibrium constant? Can you see this? You will notice that now you can write K3 as K1 multiplied by K2. Because if you multiply K1 and K2, this B and B will get cancel out, and you will finally get concentration of C by concentration of A. So we can finally say that if you add two equations, then their equilibrium constant of the final equation will be multiplication of the two added equations. Got it? That is K3 is equals to K1 multiplied by K2. Now we will move on to the second situation, which is reversing the equation. Suppose we have a reaction A going to B, for which K1 is given as B by A, so product by reactant. Then what will be the equilibrium constant for the reverse reaction? Suppose we represent the reverse reaction equilibrium constant as K2. So K2 will be now equals to A by B. So finally what we can say, that if you want to find out the equilibrium constant for the reverse reaction, then you will take the reciprocal of the previous equilibrium constant. So we can write K2 is equals to 1 by K1. This is the second situation. Moving on to the third situation, which is change in stoichiometry. How can we change it? Suppose we have this again same equation, A going to B, and for this the equilibrium constant is K1, which is B by A. Now if you multiply this whole equation by n, then what will happen to the equilibrium constant? Your equilibrium constant K2 can be now written as B raised to the power n, concentration of B raised to the power n, and it is divided by the concentration of A raised to the power n. Can we develop a relationship between K1 and K2? Is it possible? Yeah, it's very simple. What you can do, you can write K2 as concentration of B divided by concentration of A whole raised to the power n. Because the power is same, we can take both of them under the same power. Now, if you substitute this B by A with K1, you will finally get it as K2 is equals to K1 raised to the power n. Is it clear? How are we doing these three situations? Dealing with these three situations? It's very, very important that you know this. Now, I am giving you a task. Can you do a similar thing for the subtraction of equation? We have seen it for the multiplication of, addition of equation. Can you deduce it for the subtraction of equation? It's very easy. Just try this fourth scenario by yourself. Now, we'll move on to the second thing which affects the equilibrium constant. We have seen that how the equilibrium constant depends upon the balanced chemical equation. Now the temperature has even a greater role in that. To define this, I will give you an equation. Now the learning of the equation is not that much important, but the outcome is important. How is that equation written? So it is called as the Vent-Hoff equation, which says that the differential of the ln k is equals to delta H naught by RT square. If you just integrate this equation, you will get it as ln k2 by k1 delta H naught by R 1 by T1 minus 1 by T2. If you are not interested in learning the equation, no problem. But I will suggest you at least try to integrate this, because this kind of questions are asked in your exam, which is a kind of, we would say, aptitude one, where you are asked to integrate to get a very useful equation. Now, if you follow this equation, you can get several results. First of all, what are K1 and K2? They are equilibrium constant at two different temperatures, T1 and T2. Then T1 and T2 will be always in Kelvin. It's very obvious. Further, this delta H naught here is the enthalpy change for the reaction in terms of joule. And finally, your R is your ideal gas constant, whose SI unit value is 8.314 joule per mole per Kelvin. Then, moving on to the various aspects of this equation. In the first aspect, what we are considering, we are first taking this integrated equation and we are considering that delta H naught is positive. That means you are giving the energy to do the reaction, or you can say the reaction is endothermic in nature. So if delta H naught is positive, and we already know that T2 is greater than T1. So we are taking a case where T2 is greater than T1. So if T2 is greater than T1, what we will say? That 1 by T1 minus 1 by T2 will be positive. Why is it so? Can anybody think of it? Yeah, it's very simple. You are taking the reciprocal. So if 2 is less than 3, then 1 by 2 is greater than 1 by 3. So it's a simple analogy. You can calculate this value. You can get this. Similar to that, if T2 is greater than T1, then 1 by T1 is greater than 1 by T2. Therefore, their difference will be positive. So this whole thing on the right hand side will be positive because delta H naught is already positive. We have taken that case only. And if T2 is greater than T1, then this difference will give you a positive value, and R is a constant whose value is positive. So this whole thing on the right hand side becomes positive. Now to equate this given equation, you have to keep this ln k2 by k1 also positive. And there is only one way to keep it positive, that is k2 greater than k1. So this is a very important conclusion, and you must remember this also. If you are taking a ln value less than 1, then it will always give you a negative value. And if you are taking a ln value greater than 1 or greater than 0, I would say, not 1, then in that case your ln value will be always positive. So k2 will be greater than k1. So finally you can say, if you are increasing the temperature for an endothermic reaction, then the Kc value will increase. You can see that at a higher temperature, which is T2, the K2 value is greater than the lower temperature K1, whose value was T1, whose value was K1. Moving on to the second case. So we again take the same equation, the integrated form of the Vent-Hoff equation, and in this case we are taking delta H naught as negative. Now if delta H naught is negative, and we are taking the same situation of T2 greater than T1, then what will happen? This whole thing on the right hand side will become negative. You can easily think of it. Now if this is negative, that means ln k2 by k1 is negative, or you can say k2 is less than k1. So what we can say, that for an exothermic reaction, if you increase the temperature, the Kc value will decrease. See, for T1 we have a greater k1 value, as compared to the temperature T2 which has a smaller K2 value. Now this is only true for exothermic reaction. So we will now do a question on it. Here is a question for you. The following concentration were measured for the formation of NH3 from N2 and H2 at equilibrium, and the equilibrium concentrations are given at 500 Kelvin. For N2 it is 1.5 into 10 to the power minus 2. For H2 it is 3 into 10 to the power 2 minus 2. And for ammonia it is 1.2 into 10 to the power minus 2. Then you have to use your simple equation to calculate the equilibrium constant. We are given with the reaction equation also. It is already balanced. You can just check it. N2 plus 3H2 giving us 2 moles of ammonia. Your time to solve this question starts now. It's very simple. What you have to do, you have to simply put the values in the equilibrium constant. Now I am moving on to the solution. Don't worry, if you are able to put the values, that is good enough. The part of calculation can be done by anyone. You just have to know that how do we put the values. Okay, so let me show you. Now what are the things that are given in question? You are given with the equilibrium concentration of N2 and H2 and your NH3. At the same time, you are given the temperature, but we don't need it. Now, if you want to calculate the equilibrium constant K in terms of concentration, then you need to put the product concentration on the numerator and the reactants concentration on the denominator. Further, if you put this according to the equation, then you will get a square times of ammonia divided by the concentration of the nitrogen at equilibrium multiplied by the concentration of hydrogen at equilibrium. Got it? Why we now hydrogen concentration is being cubed here. Why we are cubing it? Because H2 has a coefficient of 3 in the balanced chemical equation. You can see it in the question as well. Similarly, the concentration of ammonia is being squared here because the coefficient of ammonia in the balanced chemical equation is 2. If you put the values further, then you will get your Kc value as 0.0355 into 10 to the power 4 mole raised to the power minus 2, which is your final value for the equilibrium constant. I hope you got the point. It's very easy to solve it. Just try this thing by yourself again. Moving on to the next question. Here we have a hypothetical equation where your Kc value is given as 50. Now, both for the forward and the reverse reaction in the equilibrium are elementary bimolecular reaction. Then you have to calculate the value of Kc for the reverse reaction, first thing, and the value of K"C, which is for the same reaction but with a multiplied coefficient. You can see we have multiplied the equation of A plus B going to C plus D with 2. Or you can say we have doubled this situation. How we will solve it? Now for the first situation, if you calculate the K"C, that is for the reverse equation, reverse reaction, what we have to do? We have to reverse the reaction. Upon reversing the reaction, we know it very well. The equilibrium constant now has a reciprocal value. So we can write it as K"C is equals to 1 by Kc or is equals to 1 by 50. Now this value will be calculated as 0.02. So this is your K"C value. Moving on to the next situation. In this case, we have kept the equation same, but what we have done is multiplied this whole situation by 2. If you calculate the K"C, which is the new equilibrium constant, then you will get the concentration of C raised to the power 2C rather than C, the concentration of D raised to the power 2D, the concentration of A raised to the power 2A, and the concentration of B raised to the power 2B. Isn't it? We can take this 2 common. You can see that I have put this thing 2 outside the bracket. Further, if you just put this thing as Kc, so we have this C, concentration of C raised to the power small c, concentration of D raised to the power small d, divided by the concentration of A raised to the power small a, concentration of B raised to the power small b. So this whole term inside the bracket can be considered Kc. Therefore, K"C is equals to Kc square or 50 square. If you just square it, you will finally get your K"C value as 2500. So this is your final answer. Moving on to the next question, problem 6.4 of the NCERT. In this case, you are given a Kc value of 4.24 at 800 Kelvin for the equation CO plus H2O giving us CO2 plus H2. Now you have to calculate the equilibrium concentration of the CO2 plus H2, CO and H2O. So you have to calculate it for all the species at the same temperature. If you have the initial concentration of CO and H2 as 0.1. Here you have a problem because we have not dealt with this ICE table, but I will give you a small idea with this question. Then we will look on to the procedure in the next lecture, right? How we'll do it? So first of all, what is given in the question? We are given with the value of the initial concentration, which is for CO and your H2O. And we are also given with the value of Kc, which is 4.24. Temperature is mentioned at 800 Kelvin. Now, if these things are given, can we construct a table? Suppose this was our reaction. Then according to the equilibrium, what we can say that initially we have 0.1 and 0.1 of the reactants. After some time, suppose X amount of CO and X amount of H2 has reacted. Now why we have taken it as X? Because the coefficient of CO and H2 is X. Now this concentrations that we are seeing, which is 0.1 minus X for CO and 0.1 minus X for H2O, they are concentration at equilibrium. From the balanced chemical equation, we can also say that 1 mole of CO is giving us 1 mole of CO2. So therefore X concentration will give X concentration of CO2 and X of H2. Further, what we can do at equilibrium? We can write the equilibrium constant. How we can write it? So we already know the concentration of all the species at equilibrium. So Kc can be written as CO2 concentration divided by H2 concentration. CO2 concentration multiplied by H2 concentration divided by CO concentration multiplied by H2O concentration. If you put the values here, you will get it as X square divided by 0.1 minus X whole square, which is 4.24. Now if you just solve it further, you will get a quadratic equation, which is written as X square minus X square is equals to 0.0424 minus 0.848x plus 4.24x square. Just rearrange this equation in the standard form and name it as equation number 1. Now how can we solve it? So there is a very short formula for it. If you are getting your quadratic equation, then you can solve it. X is equals to minus b plus minus root under b square minus 4ac divided by 2a. What are a, b and c? So a is the coefficient of x square, b is the coefficient of x, and c is your constant. If you compare it with the equation number 1, the standard equation, you will get a as 3.24, b as minus 0.848 and c as 0.424. Putting all of these values in the value of x, you will get this whole equation. Now, just simplify this further to get two values of x. Now, why we are getting two values of x? Because in this equation, if you see, we have two situations, plus and minus. So, for plus, you will get one x2, name it as x2, and for minus, you will get it as x1. Now, we have to neglect one of this. How do we neglect it? Now to select the possible root, we have to neglect the value which is x2 0.194. Why we are neglecting it? Because if you take 0.194, then you will result in a concentration which is having a negative value. Because the initial concentration is itself 0.1 and you can't go to a greater concentration and it's not possible, right? So for that reason, we can't take this value. Further, if we take 0.067, then we can calculate the equilibrium concentration further. For CO2, we will get it as x, which is 0.067, and for CO, we will get it as 0.1 minus x, which is 0.1 minus 0.067. So finally, we can write the equilibrium concentration of CO and H2 as 0.033, and for CO2 and H2 as 0.067. Next, can we summarize all of this? So we know that equilibrium constant can be expressed only at equilibrium state. Then it can be Kc when we are considering the concentration terms and it has a perfect numerical value at a given temperature. So we can say that our Kc varies with temperature, and we also know that our equilibrium constant varies with our equation, balanced chemical equation. Further, what is Kc? It is the ratio of product to the reactants, where products and reactants are raised to the stoichiometric coefficient. So this was all for today's class. Thank you for attending the session.